Hello everyone, this is Muhammed. I'm a PhD candidate at Texas State University. So today I'll be talking about thermal energy storage in building materials, how we can incorporate phase change materials into the building materials, how we can test them and see how it performs with concrete and other different types of building materials. So the idea and motivation is we're using a lot of energy in our buildings, in residential and commercial buildings for different purposes such as like heating, ventilation, or air conditioning. And this significantly increases the energy demand in buildings. So construction industry for both residential and commercial buildings is accounted for 32% of global energy demand in 2010, and this number increased to the 36% in 2020. And unfortunately, we are generating this energy through fossil fuels, and this mainly releasing a lot of greenhouse gas emissions into the atmosphere. And construction industry is responsible for 37% of the energy-related CO2 emissions. So the idea, we are trying to reduce both greenhouse gas emissions and we are trying to decrease the energy demand and at least like shift this energy use from peak hours to the off-peak hours. So for this, we need some innovative methods. So the thermal energy storage is one of those methods. So it's basically like we are storing and later releasing the heat energy for various purposes. So it's mainly what it does is it absorbs and it stores the excess heat when it's available, and we are using them when it's needed. So for this type of technologies, we are using some smart materials. They are called phase change materials. So these materials have ability to hold or discharge significant amount of heat energy in specific temperature range by undergoing some phase transition. So what it mainly does is, as you can see here, PCM are in, you don't see that. PCM are in solid state. When the temperature rises, the PCM melts and it absorbs a significant amount of heat and it becomes liquid. So when the temperature goes below the solidification temperature of phase change materials, it starts solidifying and it releases the heat to the surrounding environment, which prevents the instant temperature increase or decrease. So they could be really beneficial into the buildings. What they do, first of all, they narrow down the gap between the peak and off-peak hours energy use. How it does is it shifts the consumption of the electricity from peak periods. So to better understand this, we do have a figure here. So in this figure, this is to show how PCMs perform in the indoor temperature in the buildings. So the red curve represent the temperature profile with PCM, and the blue dash curve represent the temperature profile with PCM. The first one, the red one, was without, the blue one is with PCM. So first of all, what we can see is the peak temperature has been delayed with using PCM. And we see a peak temperature reduction while we are using phase change materials here. And finally, we do see a less temperature fluctuations between two types of materials. So what it ultimately does is it does save energy and it improves this less temperature fluctuation, improves the thermal comfort of occupants. And it does help us to continuously get benefit from the solar thermal energy systems, and we are ultimately reducing the cooling load during the daytime and the heating load during the nighttime or the cold seasons. So we do have different types of phase change materials that we have been using. In our research group, we mainly focused on organic PCMs. This can be categorized into paraffin and non-paraffin type of PCMs. So why we're choosing these materials, they are very compatible with building materials, and they do have a very high latent heat storage. And they do have very low thermal conductivity. That's something that we are looking for, thermal insulation in the buildings. And they do have a very broad range of the temperature, the phase transition temperature. So we do have different methods to integrate these materials into our building materials. First one is the direct integration, where we are incorporating liquid or solid PCM into the building materials like cementitious or gypsum plasterboards. The second one is the impregnation of the PCM, where we are actually immersing our hardened material into the liquid PCM, and the PCM is being soaked into the material via capillary actions. And unfortunately, these two methods they're vulnerable to the leak into the matrix, and which is ultimately affecting the performance of our building materials. So we are looking at some innovative methods. One of them is the encapsulation, where we are using either macro storage materials like tubes or like some containers that we are encapsulating our phase change materials inside this, or we are using some micro or nano polymer like synthetic or natural polymers to encapsulate our materials to prevent the leakage of these materials into our building materials. So, and finally, we do have stabilization of phase change materials. This is very like new, and we love this technology because we can further contribute to the sustainability by using this. In this, we are using some supporting materials. This can be some waste-based or recycled materials. We are impregnating our PCM into the porous structure of this waste-based materials, and we're using in our building composites. So in our research group, we have mainly focused on use of microencapsulated phase change materials and shape-stabilized phase change materials. So the idea of using these materials, first of all, these materials, like while we're microencapsulating them, we prevent the leakage of phase change materials, and we technically try to reduce the effect of PCM into our matrix, and we try not to affect the concrete performance. And also, it does a little bit of increase the higher heat transfer rates it provides us, and they're very actually thermally reliable compared to the direct incorporation methods. So we have used this microencapsulated phase change materials in different type of composites, as you can see in this figure too. We have did some cementitious composite. Like we have first mixed our raw materials, and then we have added like our chemical admixtures and water, and then finally we added some microencapsulated phase change materials, and we have casted and cured them. So we also use this in gypsum composites as well, as you can see in the figure 3. So unfortunately, regardless of the incorporation method, phase change materials affect the mechanical performance of the concrete. So that's why we thought maybe we can incorporate these materials into some other polymer structures that we can use this as an architectural element, such as like in between the wall members, or like ceilings, or like floors, or like a roofs. So we have 3D printed polylactic acid composites, and we have we did some tubes, holes, and we have incorporated our microencapsulated phase change materials in this. So as we are using a lot of PCM in this composites, definitely we're expecting more thermoregulatory performance here. So besides that, we have used some form-stable PCMs in which we have used basalt. We have produced foam concrete through this. We have used basalt powder, which is an environmentally friendly, which is a waste-based materials coming from the basalt quarries. And we have used solid capric acid as a PCM. We have melted this, and we impregnated using the vacuum impregnation technique. We have incorporated these materials into our porous basalt powder. We do some leakage tests to understand, to optimize the PCM ratio in our composite PCM. So, and we recently completed this study. It's under review. We have used recycled expanded glass. Glass is another waste-based material, and we have used N-octadecan as a PCM. And again, we used vacuum impregnation technique and tested the effect of. We wanted to see like how thermally behavior does these materials have. So we need to understand what we're going to how we are going to test these materials and what we are going to test. Like very similar to the all other cementitious materials, we want to first test like physical and mechanical properties. We are looking for workability and some mechanical performance like fluctuational or compressive test. So besides that, we need to understand the chemical or thermal properties of these materials. We are doing some differential scaling calorimetry. We are trying to understand the phase transition temperatures and the heat enthalpies of the heat storage enthalpies of these materials, how much heat that we can absorb, we can store. We're looking also at the TGA. We're trying to understand how thermally stable these materials are, and we're using some FTIR to see how this chemical structure and chemical interaction between these materials that we're producing, and we do some surface morphology through the SEM and EDS. Finally, this is a very novel and unique approach that we are using. We are using a thermoregulation test. This is a custom designed test cabin. We're producing this test cabin, and we're placing them on a rooftop under like a clear sun or like a cloudy day, and we're placing our slab members sometimes at the room center or at the bottom center. We're placing some thermocouples, and we're trying to measure the thermal fluctuations during a day or two. So as I said, unfortunately, the mechanical performance has been affected by incorporation of the phase change materials. Only even 15% of the PCM decreased the 28-day compressive strength around like a 30 to 40%. But we definitely can optimize this via getting benefit of thermal properties. So again, although we have tried like a basalt powder and capric acid shape stable PCM, it did also affect the mechanical performance. But there are some interesting results here. You can see the DSC test results. So we are testing the pristine capric acid. We are testing the basalt powder capric acid composite. And what we are doing is we are actually trying to do 500 times heating and cooling. And we are trying to see if these materials are thermally stable. Can they maintain their phase transition or heat enthalpies? So yeah, they have like both capric acid pristine PCM and the composite that we have produced have very similar heat behavior, and after completing 500 cycles of heating and cooling, we are maintaining 99.5% of its heat storage capacity. So again, we did the same for the microencapsulated PCM and the gypsum composite. So we do also do some, while we're doing shape stabilized PCM, we need to understand like if this interaction between the porous material and the PCM, is it like a physical interaction or is there a chemical bond here? So as you can see, I'm not going to go into detail about the bonds that we have observed, but the thing is, with both capric acid and the composite has quite a bit similar peaks, FTIR peaks. So this actually shows us that we don't have any new peaks while we're incorporating basalt PCM into the basalt powder. This shows us that this interaction is purely physical. We don't see any chemical interaction here. And as we look at the TGA, what we can see is the basalt powder at up to like 500 degrees, it has no mass loss. And for the capric acid, expectedly, we are losing all of its weight up to like 260 degrees Celsius. But when we incorporate this PCM into our powder, into our supporting material, we are retaining 75% of our mass, and it shows us that this is quite a bit thermally stable material. So this is our custom test cabin that we have designed. This is our test room. We are placing this to a rooftop. We are placing thermocouples, upper and lower surfaces of our specimens at the near surface temperature and this room center temperature. So we are trying to actually understand how the temperature changes during the day. So we do start this test from night to like a 1 day period. So quite a bit interesting. We do almost like measure all the temperature changes during the day. And what we are trying to see is we are using one reference specimen, one specimen with PCM, and we try to understand how PCM affects the cooling and heating load during the daytime and nighttime. I'm going to go a little bit detail into this. As this figure, you can see the temperature variation. In the A figure, you can see like for the specimen surfaces. For the B, you see the temperature variations for the room center. The black curve shows us the temperature variation for temperature profile for PCM specimen, and the red one is the without PCM. Interestingly, yeah, it's a very good result. We can see like during the nighttime for 9 hours and 20 minutes, the PCM specimen has higher temperature than the reference specimen, around like one of them is the 8.42 degrees Celsius, the other one is like around 4.45 degrees Celsius. So, and the room temperature shows us a similar, quite a bit similar result. But when we go to during the daytime, during the peak temperature hours, the PCM specimen show relatively and significantly lower surface and room temperature than the reference specimen. So what it shows us, during the nighttime, PCM release because the ambient temperature is lower than the PCM melting and solidification temperature. So the PCM released all the heat it absorbed to the surrounding environment, and it increased the room center temperature. But for during the daytime PCM, when it's going over the PCM melting temperature, it absorbs all the heat and it prevents the temperature increase. So this is even more interesting. You can see like we can see like the difference between PCM, the temperature difference between PCM and the reference specimen. So during the daytime, for the surface temperatures, it can go up to 13.3 degrees Celsius lower surface temperature that we can obtain. But during the nighttime, we can have like around 3 degrees Celsius warmer surface temperature compared to the reference specimen. This shows us that we can significantly reduce the cooling load during the daytime and heating load during the nighttime or the cold seasons. So in here we have compared different types of our studies, and yeah, definitely we're getting really good results. We have confirmed that we can significantly contribute to thermal fluctuations, we can reduce them, and we can reduce the heating and cooling load during the daytime and nighttime. So we also confirmed this with our thermal camera images. We do some dynamic thermal camera tests. I'm going to skip this. So, and this is an interesting study. We can actually go further and do some energy analysis. We can calculate the total heat needs for a building in different climates. We can do some climate adaptive tests in here. So we can change the thicknesses of our wall members, and we can we have compared this with a reference concrete, which has around like a 0.6 watt per meter Kelvin thermal conductivity, and we have our PCM specimen. What we're looking at, for example, for the region 2, for 20 centimeter specimen thickness wall can diminish, can make the total heat need 0 for a structure in the region 2, which is an oceanic climate. So this highlights the importance of the different climatic regions and the different thicknesses. We need to understand the climate adaptive techniques and technologies. So also we can calculate actually CO2 emissions caused by these materials and how we can reduce the CO2 emissions coming from the heating or like cooling loads. So again, we don't see any changes, and this also significantly changes the type of fuel that we're using for heating or cooling. So we can definitely diminish all the CO2 coming from the heating and cooling load via or optimizing our thicknesses and the use of PCM in our walls. So some key learnings, yeah, we have achieved a really good thermoregulatory test result. We have simulated this. We did some energy analysis. What we found out, we can effectively control the room temperature. We can provide higher, warmer room temperatures during the nighttime. We can provide lower, like a colder room temperatures during the daytime at the peak temperature hours. And we can definitely we can do some notable reductions in the carbon emissions by using phase change materials. What we're looking next is we want to use some other waste-based materials. We are exploring different waste-based materials which can provide us we can optimize the both mechanical and thermal properties, and we're looking for integration more like 3D printing so that we can produce like a different thickness materials to reduce the both heating and the cooling load, at the same time reduce the CO2 emissions. And we need to do more life cycle assessment to understand the economic benefits. Yeah, we did some studies about the payback periods, but we need some more comprehensive tests here. This has been a collaborative effort through the 3 different universities in Texas State University, Dr. Togay Özbakaloğlu's research group, and we have done some collaborations in 2 universities in Turkey, Barton and Karadeniz Technical Universities. And these are some information about us. Let me know if you guys have any questions.